So hi everyone, so welcome back to yet another video. So today in this video we will be discussing about this problem checkposts on Codeforces, and this problem has came in div 2 around 244 and this is rated 1700. So we will see how we'll solve this problem by utilizing the concept of strongly connected components using Kosa-Raju's algorithm. So let us get started. So the problem reads like this, that your city has n junctions and there are m one-way roads between the junctions. So the graph given will be unidirectional only, right? As a mayor of the city, you have to ensure the security of all the junctions. So to ensure the security, you have to build some police checkposts. So checkposts can only be built in a junction. So a checkpost at junction I can protect junction J if either I is equal to J, or the police patrol car can go to J from I and then come back to I. So building checkpost costs some money, as some areas of the city are more expensive than others. Building checkpost at some junctions might cost some more money than other junctions. So you have to determine the minimum cost or the minimum possible money needed to ensure the security of all the junctions. Also you have to find the number of ways to ensure the security in minimum price, and in addition the minimum number of checkposts. So two ways are different if any of the junctions contains a checkpost in one of them and do not contain in the other. So in the input in the first line we will be given an integer n, which will represent the number of junctions in total. In the next line we will be having n space separated integers. So these space separated integers will represent the total cost of building checkpost at that particular junction. And the next line will contain an integer m, and each of the m line contain two integers u and v, which will mean that there is a one-way road from U to V, and there will not be more than one road between two nodes in the same direction. And in the output we have to print two integers. The first one will represent the total minimum cost needed to ensure the security of every junction, and the second integer will represent the total number of ways in which we can do this modulo this 1e9 plus 7. Some of the examples have been given, so let us now discuss these examples one by one and see how the output is coming for each one of them. So let us now understand the examples in the blackboard. So this is the very first example given in the question, and for this example the expected output is 3 and 1. That is, the minimum total money needed to ensure the security of all junctions would be 3, and the number of ways in which we can do this is 1. So let's see how this output will be coming. As said in the problem statement, what we want is we want to secure all of these junctions. So here n is equal to 3, that is we have 3 junctions. This is the first junction, this is the second junction, and this is the third junction. So junction is equivalent to node here, right? And the amount of money that we need to spend on building a checkpost on this first junction is 1. Similarly, the amount of money that we need to spend on building a checkpost on the second junction is 2. And similarly, the amount of money that we need to spend for building a checkpost on this junction is 3. So you can imagine a checkpost as a place which controls the traffic, right? So in that way it will be protecting every junction. So no checkpost is present in any of the junction initially, so we can say that every junction initially is unprotected. So initially every junction will be unprotected, but we can protect the junctions by building checkposts at some of the junctions. So see, if I decided to build a checkpost on this third junction, so what will happen? So suppose now I have built a checkpost on the third junction, and in order to do that I have to spend a total of 3 units of money. So that's why when I built a checkpost on this junction, I have now spent a 3 units of money as demanded. So what will happen after building a checkpost on this junction? So since it was mentioned in the question, if we are able to protect a particular junction I, right, then we will also be able to protect some another junction J if they are connected. That is, if we can go from I to J and then again come back to I from J, then it means that this I and J are connected. And also if this I is protected, then automatically the junction J will also be protected. So the same thing here also. Since we have now built a checkpost on this junction, right, and from this junction we can move to this junction and again come back to this junction, so it means that this thing is connected, and if any of the junctions of this part is protected, then we can say all other junctions are also protected. So that's why we can say that this junction is now protected at a cost of 3, and this junction is also protected because this junction is reachable from 3, and then from this junction we can again go back to 3. So that's why now both of these junctions are protected, but from these two we cannot go to 1, right? So it means that we again have to build another checkpost on this first junction, because there is no way we can go from this 3 to 1, right? So that's why we have to build another checkpost on this first junction, and in order to do that we have to again spend a total of 1 unit of money. So let's add 1 to our answer. So now, as you can see, that all of these 3 junctions are now protected. Since every junction of this graph or the city is now protected, so we can say that our work is done, and that in order to do this, the total amount of money that we needed to spend was 3 plus 1, that is 4. But since in the output it is given 3, it means that we can do this in a better way, and that way will only cost us 3 units of money instead of 4. So let us now see how try to find a way of getting this 3 units of money instead of this 4. So this was the original given graph, right? And I told you initially to build a checkpost on third, that is this, and another checkpost on first, and in this way we were able to secure every junction present in the graph. But what if I had told you to instead build a junction on first and also another junction on this second? So what if I had told you to build checkposts on the first junction and the second junction instead? So if you had done this, then the total amount of money needed to do this will have been, so see, so on building a checkpost on the first junction, we will need to spend a total of 1 unit of money, so 1 for that. And then to build another checkpost on the second junction, we need to spend 2 units of money, so 2 for that. And by doing this, we simply protected these 2 junctions directly, right? But as you can see clearly that it is possible to go from this junction to this junction and then again come back to this junction. So it automatically means that this thing is also protected now. And now as you can see that every of the junction is protected, and by doing this we only need to spend a total of 3 units of money, which is the actual answer also. So it means that instead of building the checkpost on 3 and 2, we will build checkpost on 1 and 2 instead, and by doing that we will be able to secure each and every junction of the graph by using a total cost of 3 units. But why the total number of ways possible for this example is 1, and what does this 1 represent? So this 1 represents the total number of ways in which we can achieve this minimum cost of 3. Try it on your own and realize that only after building the checkposts on this first junction and the second junction we will be able to get 3. And since this is the only option, that is 1, 2, that is building the checkpost on first junction and second junction, will be able to get a minimum of 3. Since this is the only way, that's why the number of ways present for this example is 1. So let us now discuss the second example of the problem statement. So in this example we are given with 5 nodes and the expected output for this is 8 and 2. So let us see why it is 8 and 2. So what we have to do, if you remember, so we have to build checkpost on junctions, which will help us in minimizing the total cost and also protecting each and every junction, right? So what you can do here is, suppose I decided to build the first checkpost on this fourth junction. So what will happen if I build a checkpost on this fourth junction? So it will add this 6 to our total cost of building the checkpost. So plus 6 to our result, plus, since in the question it was mentioned that if we are able to go from a particular city on which the checkpost has been built to any other city, right? So in that case, those other cities will also be protected. So since we have built a checkpost on this fourth city, or the fourth junction rather, so this is protected now, and thereby as a result, this fifth junction, 1st junction and the third junction is also protected, because it is possible to go from this 4 to 5 and then from 5 to 1 and then this from 1 to 3. So we can say this whole thing is protected now just by building a checkpost on this fourth junction, right? But still this second junction is not protected. So it means that we now have to build a second checkpost on this junction, and that would cost us 8 units of money, right? And in this way this junction is also protected now, and every junction is now protected if you see. So in order to achieve this, the total amount of money that we needed to spend is 6 plus 8, that is 14. But in the example output you can see that the same thing has been done with just 8 units of money. It means that we can have built checkposts on some other pair of junctions and have achieved a better result than 14. So let us now see what those junctions would have been. So if you remember, then what we did earlier is we build a checkpost on this fourth junction and the another checkpost on this second junction, and in that way we got 14. But now what I am telling you is, instead of building it on fourth and second, build the first checkpost on this fifth junction and the second checkpost on this second junction only. So if you do that, then you will see that by building a checkpost on this fifth junction, it will cost us a total of 0 unit of money. So 0 plus the money that we need to spend in building the second junction, which is 8. So 8. So by doing this, this junction and this junction are now protected, and since we can go from this 5 to this 1 and then this 3 and then this 4 also via these paths, right? So it means that this component is now protected and this is also protected. So it means that each of the nodes of the graph is now protected, and in order to achieve this result we had to spend a total of 8 units of money, right? Which is our output also. So in this way the output for this example is 8, because we had to build checkpost on the second junction and the fifth junction, and that would cost us a total of 8 units of money. So now you know why the output for this example is 8. And also if you see, then the total number of ways in which we can do this is 2. But why? I guess some of you might have predicted, instead of building the checkposts on the second junction and the fifth junction, what I decided instead is to build the checkpost on the third junction and the second junction instead. So had I done this, then the amount of money that I needed to spend was 0 for this junction and 8 for this junction. So 0 plus 8, which is 8 only, right? And again if I had done this, then each one of my nodes or the junctions would have remained protected. So these two will have been protected directly, and since from this 3 we can go to 4, and then from 4 we can go to 5, and then from 5 we can go to 1. So in this way each one of the junction will be protected again indirectly, and thus we can say we spend a total of 8 units of money, since it is possible to get this result in 2 different ways, right? So that's why the output for this example is 2. So now I hope you have understood the problem. So let us now discuss one more example to understand it even more clearly. So let us now discuss the third example of the problem. This example is quite big, and let us now see why the output for this example is 15 and 6, right? So let us now try to build the checkpost for this component first, and then we will build a checkpost for this component. In order to build checkpost for this component, on what junction should we build? So we can build either the checkpost on the 8th or the 9th or the 10th, or multiple of these, right? So as you can see that if I build a checkpost on the 9th or the 10th junction, then we will never be able to go to the 8th junction. So it means that somehow we have to build a checkpost on this 8th junction anyhow, right? We don't have a choice. So by doing that we have to spend a total of 4 units of money. So 4 in our result, plus now we have two options. We can build a checkpost on either the 9th junction or the 10th junction, and either of them cost us 10 units of money only. So we will build it on any of them, right? So let us build the junction that is the checkpost here now, and by doing this, this junction is protected, this junction is protected, and since we can go from this 10 to the 9 and from 9 to the 10 back, so it means that this ninth is also protected. So it means that this component is now protected completely. And in order to do this, we had to spend a total of 14 units of money. But now our work is not done yet. We now have to protect these junctions also. So it means that we will continue to build the checkposts. So in this component of the graph, we can build the checkpost on one or more than one junctions, right? So suppose I decided to build a checkpost on the seventh junction. So just see what happens. So since I have built a checkpost on the seventh junction, so it means that this is protected now, and this thing will cost us 1 unit of money. So 14 plus 1, that is 15, right? And since in the question it was given that if we are able to reach from the seventh node to some other node and then come back to the seventh node, then that particular jth junction will also be protected, right? So here if you look very carefully, then you will see that from the seventh junction we can go to the third junction, and then from the third junction we can go to the fourth junction, and then from the fourth we can go to the fifth, and from the fifth we can again come back to the seventh. So it means that each of the junctions present in this path is protected also, right? So this third is also protected now, fourth is also protected, and fifth is also protected. Similarly, if I had followed the path from this seventh junction like this, that is from 7 to 3, then from 3 to 4, then from 4 to 5, then from 5 to 6, and then from 6 to 4 again, then from 4 to 5, and then from 5 to 7. Then again in this way, this sixth junction will also be protected, right? Or if I had followed the path of, if I followed this path, that is from 7 to 3, then from 3 to 1, then from 1 to 2, then from 2 to again 3, and then from 3 to 4, and 4 to 5, and then 5 to 7. So in this way, this junction and this junction will also come into the protected list, right? So it means that from this seventh junction, it is possible to go to every other junction and come back to it in this particular component, right? And by doing this, we were able to protect each of the junctions present in the graph, and that costed us a total of 15 units of money. So that's why 15 is given as the output for this. So if you have noticed, what we are doing here actually, for a given strongly connected component, so for this example, this was a strongly connected component, this was a strongly connected component, and this was a strongly connected component, right? So for each of the strongly connected component, we are just taking the minimum of the values of the nodes present. So since for this strongly connected component, the minimum that was present was this one only, right? And this one was present in 3 places. So it means that in order to protect each and every junction of this component, we need to spend just 1 rupee, because by spending that 1 rupee on that particular junction, we will be able to reach every other junction and thereby protecting all of them also, right? So that's why for each of the component, strongly connected component rather, we will take the minimum value of it. So the minimum we got for this strongly connected component was 1. For this we got 10, and for this we got 4. So that's why 4 plus 10 plus 1 was 15, which was our output. Because what is our ultimate goal? Our ultimate goal is just to minimize the total cost of protecting every junction, right? If this is a strongly connected component, it means that we can build just one checkpost on any junction, and from that junction we can reach any other junction and thereby protecting that other junction also, right? So that's why for each and every strongly connected component, we will just build a one checkpost on any particular junction, and we want to build checkpost on such a junction whose cost for building checkpost on that junction is minimum. So that's why when we wanted to build a checkpost for this component, we wanted to either build it on this 7 or this 5 or this 1. Then only we will be having a total minimum cost of 1 for this component. Similarly, when we wanted to build a checkpost for this junction, since both would have costed us a total of 10 units, so that's why we can have either build it here on 10 or on 9th, right? And since in this component we had only just one junction for building the checkpost, so we built it here only, right? Since we also wanted to find a total number of ways of building the junction, so let me mark this strongly connected component. So these were three strongly connected components, and I told you that out of every strongly connected component we will take the minimum value. Why? Because it is very logical that whenever we will be building a checkpost on a particular junction which has the minimum cost of building, then it will be possible to reach every other junction from that junction also, right? So that's why we'll be building it on the minimum cost one. And we saw and for this component it was 1, for this component it was 10, and for this component it was 4. And also we wanted to find the total number of ways of doing it. So the total number of ways of protecting each and every junction present in this particular component, that is this one, will be 4 only, will be 1 only, because we can just build a checkpost on this 8th junction only. So that's why we can say for this it is 1. And since here we can have built the checkpost on either this or this, so we can say we have 2 ways, so that's a 2 for this. And similarly, since we could have built the checkpost here or here or here, that is 3 ways, so we can say 3. So 1 into 2 into 3, which is 6. So that's why 6. We will be doing mainly 3 things in the solution. So the first step is to divide the given graph or to decompose it into strongly connected components. So as you saw that for this example we divided the given graph into 3 different SCCs, right? And after doing it, what we want is we want to find the minimum value for each SCC. So we saw that for the first component the minimum was 4, for the second component the minimum was 10, and for the third the minimum was 1, right? So we want to do this only. So the first and the second step is done, and after doing these 2 steps what we will do is, along with finding the minimum value for each SCC, we will also be counting such number of minimum values, right? So as you saw that in this example the total number of minimum values for present was 1 only. For this component the total number of 10s present was 2, and for this component the total number of 1s present was 3, right? So in order to calculate the total number of ways in getting this 15 as a minimum answer, we will simply multiply the total number of count of these minimum values for each component, right? And ultimately we have to do a modulo with 29 plus 7, since this number of ways can get pretty large, right? So these 3 were the main steps that we'll be doing in order to find our total number of ways and also the total minimum cost, right? I hope you know how to divide a given graph into SCCs, right? Because I have covered the same thing in one of my previous videos also. So let me show you that video. So here if you see, then in this question, that is coin collector, I have used the same concept of strongly connected components, SCC, right? So the same thing we'll be doing here also. So I will not be explaining you from the very basic, like how to construct an SCC for a graph, right? So it will be better for you if you know it beforehand. So once I have constructed the SCCs for a given graph, I would have also calculated the minimum for each of the component, and once I have calculated the minimum for each component, I would have also calculated the total number of such minimums for each of the component, right? And at last I would just have returned what? I would have returned the minimum, that is a summation of this minimum value for each component, comma, the product of the count of such minimum values for each component, right? So I just have to return this, and particularly I have to return this with 29 plus 7, since the number of ways can get pretty large. So now I think if I write the code in the code editor, then it will become very clear to you. So this question was not very difficult one, and that's why it is rated 1700 only. So I hope you understood these 3 examples very clearly, and I tried my best to explain you the examples with the visuals. Let us now go to the code editor and code it up. So these are my given inputs, and the expected outputs are as follows given. So I have taken all the 4 examples of the problem statement. So let me start writing the code for you. So as I said, what we'll be doing, so initially we have to take the input. So in the input we first have to take a number of junctions, and then space and space separated integers, and then the next m lines, right? And also I'll be using long instead of int in every places, right? So the number of junctions, and then I have to take the input for n integers, right? So I'll be storing these integers, let's say in a vector. So this, and after doing this I have to take the input for m lines. For each of the m lines I will be having two integers as the input. So I'll be storing the same in an adjacency list. Let's say it as graph g. So g of u dot pushback v, right? So it would be a adjacency list like this, and it will be of the size n+1 because I'll be using one based indexing everywhere. And now after this, what we used to do, as I told you in the explanation, that what we have to do is we have to divide the graph into SCCs, right? So in order to do this, I'll be using Kosa-Raju's algorithm, right? So if you remember, what we used to do in Kosa-Raju's algorithm is we first store the order of the nodes in which they will be visited in order of their end time, right? And then I simply reverse the original graph and then perform the DFS again, but by the order of the elements present in the top of the stack, or those elements who finished first according to their end time. So the same thing I'll be doing here. So for that I'll be using a stack in order to store the end times, or rather the store the nodes according to the end times, right? So let's name it as st, and I'll also be using a visited array, right? So viz, and it will be of the size n+1 only, and all elements will be initially unmarked, that is every element is initially unvisited. And then I'll be iterating from the first element till the last element, and I'll just be checking if this is visited or not. So if this junction is not visited, so we'll call the DFS, right? So DFS, and what parameters I'll be passing is I'll be passing the current node, I'll be passing this visited array, and I'll be passing this graph as well, right? And also be passing this stack. So now let me write down this DFS function. So it will be a void type because it don't have to return anything. So let me write down the parameters quickly. What we will do now is we will simply mark this current node as visited, and then I will simply iterate through the childs of this current node, that is g of this node, and I will just say check if this is not visited. So if this child is not visited, then I will again call the DFS function, and this time my node will be this child, and the visited array will remain same, g will remain same, and stack will remain same, right? And after doing this, the main objective of this DFS function is to store the node while backtracking. So I will say st.pushback, or rather st.push this node, right? So in this way I have written the complete DFS function, and this will be storing the nodes according to their end time in this stack, right? So after this has been done, what we used to do in the Kosa-Raju's algorithm, so we used to reverse the graph, right? So in order to reverse the graph, what I'm saying is just use another adjacency list, reverse g, right? And it will be also of the size n+1 only, but I think instead, in place of doing it here, I can simply have done this here only. See, so when I was directing the edge from u to v here for this original graph, I could have simply said reverse of this g of v dot push back this u, right? So in this way I would have simply constructed the reverse graph here only, and don't have to explicitly construct it there, right? But now since this visited array is modified, now I again have to reassign it to 0 values only, because I have to use it again in the second DFS call, if you know how the algorithm works in case of Kosa-Raju's, right? So I will say visited dot assign the n+1 back to 0, right? After this has been done, what we used to do, if you remember, we have to start popping the elements from the top of the stack now until the stack is empty, right? And let's say the top element this time is st.top, and after taking the top element we have to pop it also from the stack so that the next element can be used next time. And I will say that if this is already visited, So if this is already visited, I won't continue, right? And if you are having a trouble with maintaining a pace that how I am doing these things quickly, then I will recommend you to study the algorithm beforehand and then only continue this video, because these things are very easy. So and I also have explained the same thing in very detail in the previous video, as I told you. So that's why I'm not explaining it here again and again. After doing this, we used to make a second DFS call, and we'll make this DFS call from this IT if this is not visited, and I will pass the reverse graph, that is this, and I will again pass this visited array, right? And I will be passing one more thing, that is I will also be passing this vector say component. So what does this component vector will be storing? So this component vector will be storing nothing but the total elements present in a particular component, right? I will be passing this here. So let me write down this dfs2 function here. So these are the parameters, and wherever possible pass it with reference, right? So now what we will do is we will mark this node as visited, and after this we will also push this or store this node in this component. So I will say component dot push back this node, right? And after doing this, I will simply iterate through the childs of this node, that is reverse graph of this node. So this is the child, and if it is not visited yet, then I will say call the same function again, and this time the node will be my child, and the visited array will remain same, the reverse graph will remain same, and the component will also remain same, right? So in this way I think I have written the second DFS function also. So this is the very basic of Codeforces algorithm, you must be knowing this. So now what I will be doing is I will be simply iterating through each and every element of a given strongly connected component, which is right now stored in this component vector. So I will say for auto child belonging to this component, and in the input, if you remember, then we also took the input of values of I. So it means that we already know what is the value associated with each of the node initially in the graph, right? So I'll be using the same thing here also. So I'll be saying the value associated with this child is less than what I have got till now. Let's say it mini. I will declare this very soon. So I will say that my new minimum value is equal to this, right? And since I'm getting it for the first time, so I will say count is equal to 1, since I got this minimum value for the first time, right? And if this is not the case, it means that we only have two possibilities left, that is this values of c will be equal to this mini, or the values of c will be greater than mini. So what we want that if this values of c will be equal to mini, then it means that we have got some minimum value before, and now we are getting the same value, right? So our mini will not change, but the count value will increase. And even if this is not true, it means that values of c is greater than mini. So for that case we will do nothing, right? So just say like 0 equal to 0. So it does not have any significance, right? Now I think I should also declare this count and mini. I will say that the value of mini initially will be int max, since I have to minimize this, and the count value will be initially 0. And now after doing this all, suppose I have explored the whole component that is a given cc, and after that I have found the minimum value of it and its count. So if you remember, then we just wanted to add this minimum value and multiply this count value every time, right? So let me declare this globally, where I will store the global results. So I will say that minimum cost to add will be equal to initially 0, and also the number of ways of achieving this minimum costs. So since I have to multiply it continuously, that's why I'm taking it 1, right? And now what I will say is this minimum cost to add will be equal to whatever value is present in it before, that is the total amount that it has gathered from other components already, plus this minimum value, right? And also the total number of ways, that is the number of ways, will be equal to whatever the number of ways it has gathered from the previous strongly connected component into the thing it has gathered now, into the count of such minimum values it has gathered now, that is this count. And And if you remember, then in the question it was asked us to modulo the answer, that is the total number of ways, with this, that is 199 plus 7. So let me declare this globally also. So I will say const int mod would be equal to 199 plus 7 now, right? And now just take the modulo of this. So I will say number of ways modulo this would be equal to this. And once I have done this, I think we have correctly calculated the total number of ways of finding the minimum value and also the minimum cost in order to build the junctions. And once I have done this for each component, then this loop will again iterate, that is this while loop, and it will again call the dfs function, and then it will again calculate the next strongly connected component, and then again it will evaluate these things, that is the minimum value for each component and and its count, right? And after that, adding it to the already existing values. And after this, I will finally print what? So I will print minimum cost to add the number of ways of doing it, right? And after this, just do a return. So now I think I have written the complete code, and I think I did a very silly mistake here. So since I'm taking the input values of I like this, so I think I should have given the size also initially, so n plus 1, right? So that's why I think it was giving a wrong output before. So now if I run the code, let's see. So as you can see, the first test case is getting passed, the second is also right, the third and fourth one are also right. So as you can see that every test case is getting passed here with this code that I just wrote for you. So now if I try to submit the same code on Codeforces, let's see. So as you can see that the solution is accepted. So this is the code that we just wrote. So what we did is very simple. We simply divided the graph or decomposed it into different strongly connected components, and for that we used Codeforces algorithm. So in Codeforces algorithm, what we do is we use two DFS calls. So in the first DFS call, we stored the order of the nodes according to their end time in this stack, right? And then we started doing the second DFS call one by one from the top of the stack, right? And then after this second DFS call function returns, this component vector would have stored every element of a given SCC. And since we already knew the values associated with each given junction here in the values array, so just we compared it with the previous obtained value, that is values of this child is less than mini or not. So if this is a new minimum value that we are getting, so that's why since we are getting it for the first time, we set it to 1, otherwise we just incremented the count, and we did it for all the SCCs and added and multiplied the results like this, and took the modulo since it was asked in the question, and at last just printed it. So I really hope you understood the problem very well, how we used Codeforces algorithm straightforward in order to solve this problem, and just followed 3 steps in order to do it. So if you found this video helpful, please like the video, subscribe the channel, because it takes a lot of efforts to create each and every single video, and I'll be uploading more and more videos related to different advanced topics in the upcoming days. So if you want that, please subscribe the channel. So thanks a lot for watching this video. Thank you.